Hello, guys. Let's talk about an interesting topic today, chemical kinetics. It is the study of reaction rates, or in other words, it is the study of the speed at which reactions take place. So, when I think about chemical kinetics, I always imagine a reaction which has two reactants and they need to collide in order to form the product. So if I can increase the number of collisions, I can make the reaction produce the product faster. And there are several factors that affect this. For example, the physical state of the reactants. If I have a homogeneous reaction where I have liquids and gases, because those molecules are more mobile, I'm going to have generally faster reaction rates. On the other hand, if I have heterogeneous reactions involving solids, those are going to be generally slower, and I can increase the rate if I increase the surface area of the solid, for example, by using fine powders. Now, obviously, the concentration, if I have more molecules, most likely they are going to collide faster, so that also going to increase the reaction rate. How about the temperature? Well, we know that the temperature is just simply the average kinetic energy. So at higher temperatures, my molecules are going to be moving faster, so this also going to increase the reaction rate. On top of that, we can add a so-called catalyst. It is a substance that increases the rate without itself being consumed. Catalytic reactions are very important in biological systems, and we are going to talk about them more later. We can also add so-called inhibitors that slow the reaction down. All right, I hope this makes sense so far. So let's take a look at an example. Let's say that I have a reaction, A reactant forming B product. At the beginning of the reaction, where my time is 0 seconds, I'm going to have 10 moles of reactant A and 0 moles of product B because it didn't form yet. Now, if I take 50 seconds, I check again the concentration, and I'm going to see that at this point I have 5 moles of A and 5 moles of B. So some A got consumed and some B got produced. And at later time, I even used up more of my reactant and produced more of my product. Now, in order to figure out the average speed, I can simply take a look at the change in concentration over time. So let's look at the average rate of appearance of B, the product, from let's say T1, which is 0 seconds, until T2, which is 50 seconds here. I need to take the change in concentration of B over the change in time. So the change in concentration can be given with delta, and the concentration is defined with square brackets. So concentration of B over the change, again, delta in time, which is going to be T. The concentration here is generally molarity. Okay, so mole over liters. Now, in more detail, I can say that I need to take the concentration of B at T2, okay? So B at T2 minus the concentration of B at the beginning, T1, over T2 minus T1. So those are simply the changes. Now, what is the concentration? At T2, I have 5 moles of B and I have a volume of the solution of 1 liters. So my molarity is 5 mole per liters at this point. So you can simply plug that in. So 5 mole over liters, right? Because of this 5 right here. Minus, what is the concentration of B at T equals 1? At 0 seconds is 0 moles of liters, right? So 0 mole per liters over the time. T2 is 50 seconds minus 0 seconds. So if I do this calculation, I'm going to get 1 molarity, right? The mole per liters over seconds. Okay, I hope this makes sense. What if we study the same reaction, but looking at the average rate of disappearance of A? So first, let's think about the speed of a car. Can you go with negative speed? No, right? So you are either staying in one spot and your speed equals to zero, or you are going somewhere with some kind of average speed, which is going to be a positive value. So similarly, the reaction rate cannot be a negative value, it should be a positive one. So I need to add a negative sign here in order to calculate the rate for the disappearance of my reactant. Why? Let's take a look at the calculation. So let's do the same calculation that we did for the product B, but now for the reactant A. I need to take the changing concentration of A. So the concentration of A at T2 is 5 moles per liter, right? So 5 moles over liters minus at T equals 0, 10 moles per liter. Now, if I subtract 5 minus 10, then I'm going to get a negative value. So I need to add this negative sign right there. And what is the change in time? Again, 50 seconds minus 0 seconds. So if you do this calculation, you are going to get 1 molarity over seconds. So this is actually exactly the same value that I've got for the average rate of appearance of B. So in this case, the average rate of disappearance of my reactant and the appearance of my product equals to the same value. Why? Because my reaction stoichiometry is actually 1 to 1. If I had 1 mole of A, I formed 1 mole of B. Now, what happens if the equation is not 1 to 1? Let's take a look at this general equation right here, where I have reactants A and B forming products C and D. And these here are the coefficients in my reaction. So if the rate equals to minus 1 over A, and this is the coefficient in A in my reaction, multiplied by the change in concentration of A over time, then I can also express the rate as minus 1 over B, which is my coefficient next to my reactant B, multiplied by the change in concentration in B over the change in time. Now, this is also going to equal to 1 over C, which is the coefficient next to my product C, multiplied by delta change in concentration in C over change in time, which also equals to 1 over D, which again my coefficient next to my product D, multiplied by the concentration change in D over change in time. All right, I hope this makes sense. Let's take a look at the practice question. How is the rate at which N2O5 disappears related to the rate at which the products appear in this reaction right here? So my rate, if I take a look at the disappearance of my reactant, going to equal to minus, right? Because this is a reactant. 1 over 2, because 2 is my coefficient right here, multiplied by the change in concentration of N2O5 divided by the change in time. And then this should equal to 1 over 4, 4 because I have a coefficient of 4 right there, multiplied by the change in concentration of NO2 divided by the change in time. And this also equals to, what do you think? Can you guess it? Simply the change in concentration of my other product O2 over time, and there is no additional fraction involved because I'm forming 1 mole of O2 in this reaction. Okay, I hope this makes sense. Now, actually, it is really useful to take a look at how my reactant disappears over time, and I can make a plot from here. So if I have my reaction with which I started, a reactant forming B product, I can plot the concentration of A as a function of time in seconds. So here are the concentration values, and you can see that as the time goes by, my concentration goes down. And what happens to the average rate? What do you think? As the concentration decreases, the rate should also decrease, right? Because I'm going to have less molecules. I hope this makes sense. So, for example, this first average rate right here is the rate as I go from 0 to 25 seconds in average. And then the second value here is the rate when I go from 25 to 50 seconds. All right. Now, chemists are not always interested in the average rate, but we are often interested in the so-called initial rate. And the initial rate is the instantaneous rate at the time 0. So right at the beginning of the reaction. Now, how do I figure out the instantaneous rate? That's the rate at which the reaction takes place at a specific time. So let's say here 150 seconds, right? So that's right there. What I can do, I can actually draw a straight tangent line to the curve at the time of the interest. And then I can form a triangle. So in this case, I know that this part will represent the change in concentration of A, right? So that is my y-axis. And this part right here will represent the change in time, which is my x-axis. And I can simply calculate the slope or the instantaneous rate from these changes. So again, because I'm talking about the disappearance of a reactant, I need to use the negative sign right there. So this whole thing will equal to minus the change in concentration of A is going to come from the figure. So what is the concentration of A at T2? What is my T2 first? Well, my T2 is going to be 200 seconds, right? Right here. And the concentration, if I look at the line, is actually going to be right here. So it's about 0.085 mole per liters. Now, what is the concentration at T1? T1 is going to be 100 seconds. So that's approximately going to be 130, 0.130 mole per liters, right? It's right between these two values. All right. And on the bottom, I'm going to have the change in time. I said I went from T2 200 to T1 100. It's 200 seconds minus 100 seconds. Now, if you do this calculation, you are going to get 4.5 times 10 to the negative fourth molarity over second. Does this value make sense? Well, we got the instantaneous rate at 150 seconds. Let's take a look at the average rate around this time on the previous slide. So 150 seconds is right here, and I see that as I go from 100 to 150 seconds, my average rate is 4.88 times 10 to the negative fourth, and as I go from 150 to 200, my average rate is 4.04 times 10 to the negative fourth. So the value that I've got, 4.5 times 10 to the negative fourth molarity per second, is very reasonable because it's kind of in between the two average values. All right, I hope this makes sense. See you in the next video.